Next, condition motion synthesis requires the model to generate 3D motion sequences conditioned on the input natural language descriptions. Previous works mainly rely on single action label or coarse action level descriptions. Such description contains limited semantic information and unable to guide detailed fine-grained motion generation for long and complex actions. Different from previous works, our model focuses on generating natural motions conditioned on fine-grained atomic action level descriptions. Here are our preprocessing steps for input annotations. As is shown here, the translucent rectangles represent original temporal segments, the brackets represent segments after preprocessing, and the text above brackets are natural language descriptions of each segment after prompt engineering. Our model takes in both natural language descriptions and motions during the training stage. For the language part, it takes in both ground truth and synthetic descriptions. Synthetic descriptions are generated through rule-based methods based on ground truth descriptions. On the motion side, it also takes in both ground truth motions and synthetic motions. Synthetic motions are generated through mirroring or speed tuning operations based on ground truth motions. The atomic action generation subnet is designed to generate motions of single atomic actions. During each training iteration, it will generate 4 motion sequences conditioned on 4 different input modalities. As is shown here, the red translucent rectangle represents conditioned input modality and activated modules, and red rectangle represents the corresponding generated motion. Specifically, the model will generate motions conditioned on ground truth motions, synthetically generated motions, ground truth action descriptions, and synthetically created descriptions. The generated motions of atomic actions will be optimized by reconstruction loss, KL loss, and contrastive loss. The atomic action connection net is designed to connect and refine motions generated by the subnet we just introduced. As is shown here, it takes in generated motions and contextual motions stored in the motion cache and generates the final outputs. During inference stage, the motion encoder is deactivated and our model only requires natural language descriptions and durations of each atomic action component. Our model will firstly generate motions of target atomic action, then connect and refine it with generated motions of contextual atomic action components. This step will be applied autoregressively to get the generated motions of full action. In this work, we train and evaluate our method on 2 open-source benchmarks, KIT Motion Language and Babel. As is shown in Table 1, we evaluate our method with 2 different settings of input on KIT-ML. When taking in the full action description, we find our model still outperforms all previous SOTAs with noticeable margins. When enabling the model to take factorized descriptions, our method gains significant improvement, where it almost doubles the performance against previous SOTA TMOs on all 8 metrics, which shows the superiority of the idea of factorizing actions into components of atomic actions. As is shown in Table 2, our method consistently outperforms in all 8 metrics. On average, our method is 42% better than TMOs and 36% better than Teach. It also achieves the best performance under another setting of metrics in Table 3 when compared against another previous SOTA MACV. The motion sequences generated by TMOs contain lots of foot sliding and the person is floating in the air. Ours, however, generate a much more natural and smoother sample. Meanwhile, the motion sequence generated by EMS contains both segments of bent over and lift. But TMOs only generates the segment of bent over. Compared against TMOs, the legs movement generated by EMS is more natural. Moreover, EMS correctly generates the transition from sits to rests. However, TMOs doesn't generate such motions. When generating motion sequences for long actions, our method shows more superiority against TMOs. As is shown below, TMOs tends to generate average poses when the duration increases. Although all atomic actions T-pose, rotate wrists, bend at elbows, and rotates arms forward ever appeared in the training set, their combination is an unseen action that only appears in the validation set. In this case, we show that TMOs can't explicitly model the functioning scope of each adverb. For example, it airily applies the in place to walks backwards, and airily creates a forward or backwards motion for later XXX in place atomic actions. Meanwhile, it can model the semantic information well when given a long sentence, which significantly deteriorates the quality of its generated motions. In this example, we show that our model can successfully control the body parts the person used i.e. tosses ball with left or right hand, hold ball with left or right hand, and kicks ball with left or right foot in each atomic action when given detailed natural language descriptions. In this example, we show that our model can independently control the speed i. quickly or slowly of generated motions of each atomic action segment through taking in detailed natural language descriptions. In this example, we show another example that our model can control different types of attributes, both motion, speed, and body parts at the same time for different atomic action segments conditioned on the natural language descriptions. Our method can generate sequences of unseen complex actions from unique sequences of known atomic actions with independent attribute settings and timings applied. However, it still requires the atomic actions are ever learned in the training set. We find many atomic actions only appear in the validation set, and our model can't generate solid motions for them. One possible solution is integration with zero-shot learning methods. Although the training set contains fairly enough samples, 1,340 turnaround segments, we find our method still doesn't perform that well on generating turnaround motions. As is shown in the example below, the generated turnaround motion is just rotating the figure around z-axis, which is different from what people will naturally do in the real world. Turnaround seems a simple motion. However, it contains lots of details, which makes its generation pretty challenging. The problem widely exists in almost all recent works, which may require a more powerful motion synthesis and language backbone.